Alright, this is number 1 from the AP Physics B 2011 Form B exam. And we're dealing with a mechanics problem. We've got a person pushing a box up an incline at constant speed to a vertical height of 3 meters above the ground. They're going to be pushing with their force parallel to the plane. We know the mass of the box is 50 kilograms, and we know the coefficient of kinetic friction between the box and the plane is 0.3. First part, we'd like to do a free body diagram. We've got weight on the block. It's straight down. I'm going to label this one mg. I've got a normal force coming perpendicular to the plane. We're pushing the block up the plane. I'm going to label that FP for pushing force. So I could have done an A for applied force. And finally, we've got friction, which is resisting the motion of the block. So that's going to be down the plane. This part was worth 4 points. You actually get a point for each one that you do correctly. You won't get that point if you don't label it, so you have to have all 4 labeled. You're actually going to lose points for every incorrect vector that you draw, or anything that's in the wrong direction, etc. B wants us to determine the actual normal force acting on the object. For that, I'm going to redraw the free body diagram over here. I don't want to change what I've got already drawn, so I'm going to just quickly show this block with its normal force perpendicular to that plane. And I'm going to draw only these two forces, the weight and the normal force, because I want to break up that weight into my x and y components, which we could label as mgy and mgx. And remember, those are the two components of the weight that are perpendicular and parallel to the plane respectively. So mgy is the perpendicular component of weight and mgx is the parallel component. When you draw this, you see that the normal force and weight are the only two forces in the y dimension. So if I apply Newton's second law or my dynamics set up to the y dimension, first I know it's in equilibrium, and I'm going to say it comes from my normal force, which I'll be calling as positive because it's out of the plane. And then I'm going to subtract that y component of gravity, which means the normal force is equal to the y component of gravity. Because that y component of gravity is adjacent to my angle theta, I'm going to take mg and multiply it by the cosine of my angle theta. For my final normal force to equal mg cos theta, I'm going to use g as 10. So it's going to be 50 times 10 times the cosine of my angle, and that angle is given in the diagram of 20 degrees. Alright, 1 second, let me go ahead and calculate this. And I'm going to get a value of 470 newtons. I'd get a smaller value if I use 9.81. This problem was worth 2 points. Basically, you get the point for identifying the proper setup using dynamics, and the point for the answer. Alright, for C, we would like to figure out the component of the force of gravity that's parallel to the plane. And for that, we're going to utilize our simple trigonometry here. We're going to look in this triangle that we drew up on the incline, and we're going to see that the parallel component is the x component of gravity. As a result, mgx, being opposite of my angle theta, will equal mg sine theta, which is 500 times the sine of 20, and that ends up being 171 newtons. And again, if we were using 9.81, we would get a smaller value. C was also worth 2 points. And now on to D. For D, we'd like to calculate the friction force between the plane and the box. Now at this point, we don't know all of our X forces. We have the pushing force, the parallel component of gravity, and that friction force. So I can't just look at my dynamic setup. What I'm going to have to do is utilize my force of friction equation. So for D, I'm going to say the force of friction is mu Fn. This is kinetic. And Fn, we already found over here in part B. So we're just going to take 0.3 and multiply that by the normal force of 470 newtons. And that is 141 newtons. I'm going to go ahead and shrink some of this stuff because it's getting to be in the way. Alright, E, we want to calculate the force applied by the person on the box, and that's that third force now in that X dimension. So we can apply our dynamic setup. So I'm going to do that. I'm going to say the net force in the X dimension is 0. It's going to come from, I'm going to treat the left as positive here. I'm going to say my pushing force is the positive force, and I'm going to say the opposing forces are negative. So that's going to be the friction force. That's down the plane. And that component of gravity that's parallel to the plane, so mgx. So my overall pushing force ends up being my friction force plus mgx. And we know both of these now. We know the friction force is the 141 newtons we just calculated, and mgx is the 171 newtons we calculated in part C. And when we add these together, we get an answer of 312 newtons. And part E was also worth 2 points. Sorry, part D was also worth 2 points. Both. So far, they've all been 2 points except for that free body diagram in the beginning. And then finally, for F, we need to figure out the work done by the person on the block. So for that, our best bet is to just use the simple, straight-up, normal work equation of work equaling force times displacement. Just make sure you're using it correctly. Make sure you're using the right forces and the right displacement. So let's take a look at this a little bit closer. The work done on the box will be FD cosine theta, or really FD times the component parallel to each other. And if we look, over here up at the box, we know the person is pushing the box up this entire incline. Up the incline here. And that incline distance is the distance we need to use. Well, they didn't directly give us that distance, but they did give us 2 parts of our right triangle. We know the angle of the incline, and we know this leg that's opposite. So our first job is to figure out either D or D cos theta, however you want to go about labeling this portion. I'm going to call it distance. I'm going to say the distance that the object actually travels is the hypotenuse of this incline. And we know the opposite leg, so we're going to use sine. And so if we know the sine of an angle is opposite over hypotenuse, then we know the hypotenuse is the opposite angle over the sine of that angle, or the opposite leg over the sine of the angle. So that's what I'm going to be using here. I'm going to say D is the height, I'll call that my y distance, divided by the sine of theta. So this could be 3 divided by the sine of 20. And that's going to be this whole d cos theta part, because I'm going to use the F that's actually pushing it up the plane. So let me first find D. No. That's 8.77 meters. Now I can go ahead and use my overall value for work. I want to know the work done by the person pushing the box. So I'm going to go ahead and use the pushing force, 312 newtons. And I'm going to just multiply it by the 8.77. To get a final work value of 2,737 joules. And F was also worth 2 points. Now let's take a look at this point breakdown, because I find this to be actually quite peculiar. And also, by the way, as long as 3 of your answers have all proper units, no incorrect units, you get the 15th point. So if you look at it, it's all going to add up to 14. But what I find to be the interesting part is part A, worth 4 whole points for just the free body diagram. There's no math. All you got to do is have that free body diagram labeled, and you're going to get 4 points. So keep that in mind when you're doing these problems.